Oh, is it not on Bruin? You know what? Probably published it for one class, but not the other. Pop, pop, pop. Oh, yeah, here we go. Sorry. Publish. You gotta do that. Okay. Now it's on Bruin Learn. Well, it was. It just wasn't published, but... but yeah, I guess that's what matters. All right. Well, happy Friday. It's Friday of week 9. This is like home stretch. I hope you guys are doing well. And all right, well, let's take a look. So today I want to talk more Bootstrap. This time I want to do it with library boot. Okay, so on Wednesday we talked about Bootstrap being a way for us to simulate the sampling distribution by resampling our data. So, both the randomization test and Bootstrap resamples our data. The randomization test shuffles our data, so all of the observations are used again, but just kind of reshuffled. Whereas Bootstrap resamples with replacement. And resampling with replacement is effectively the same thing as taking your existing sample and creating infinitely many duplicates. So you're saying, I'm assuming that the sample I have is representative of the population, and therefore if I want to simulate the population, I can just take my sample, clone it maybe like 1,000,000 times or 1 billion times, and now I have this big population, and then I can draw a sample from that fake population. And that's what we do with Bootstrap. Anyway, I showed you a little bit of code on Wednesday on how to do Bootstrap, kind of like if you were to write your own for loop. And we'll see for loops again today, but I also want to introduce package boot. Okay, so package boot provides a few useful utilities. And also, if you kind of go online and you just say like Bootstrap tutorial in R, a lot of your resources are going to make reference to package boot. This is kind of the package to use to do Bootstrap in R. And so it's good to be familiar with it. And then there's other packages that rely on package boot to then create other kinds of related analyses and things like that. So anyway, you can do that doing install.packages boot, and then you load it up using library boot. And boot can perform both non-parametric and parametric Bootstrap. Today's examples will just kind of focus on non-parametric Bootstrap. But yeah, this is kind of what it looks like. All right, so if you go and you ask for the help on boot, this is the description that comes up. You can also just go to our library boot, just search for that, and it will. This will be kind of the manual here. Okay. And that's what we have. And you can just kind of go down to boot here on page 11 to read the description. Okay, so here's the description along with kind of its usage. So it's kind of a long entry in the manual pages, and if you have it loaded in R, you can always ask help on boot, and this is the output. But the description says for boot, generate R Bootstrap replicates of a statistic applied to data, R here being whatever letter you specify, whatever number you specify for the argument R. It can be both parametric. It says both parametric and non-parametric resampling are possible. For the non-parametric Bootstrap, possible resampling methods are the ordinary Bootstrap, the balanced Bootstrap, antithetic resampling, I have no idea what that is, and permutation. For non-parametric multi-sample problems, stratified resampling is used. This is specified by including a vector of strata in the call to boot. Importance resampling weights may also be specified. So this stratified resampling you can kind of force in certain I guess, preferences or tweaks to make sure your resamples look a certain way. So let's say, for example, in your original data, there's a particular, I don't know, just for example, a gender split. Okay, so in your original data, maybe it's 70% male, 30% female, or something like that. And when you resample your data, you kind of, for whatever reason, perhaps you want to preserve that kind of gender split in your resampled data. And so you can do that using stratified sampling. And what stratified sampling will basically say, these 70 observations belong to this group, these 30, or not, this 70% belongs to this strata or this group, this 30% belongs to this strata or that group. And when you resample it, we want to make sure our resampled also has 70%, 30% split like that. Because if you don't specify that and you do resampling, just random resampling, you might end up getting, just by random chance, like a 65-35 split or a 75-25 split or something like that. And that could end up kind of throwing off your results because of random sampling. And so that's a possibility. You can specify that inside strata. You could see the default specification for strata is just repeat 1 n times, so that would put everybody into the same strata. But you can, again, say, repeat 1 70 times and then repeat 2 30 times, and that would apply to a case where you have 100 data points or something, and 70 of them are group 1 and 30 are group 2. Okay. You'll see that the arguments data, statistic, and R do not have default values, so you do have to specify those. But everything else here does have a default value. And again, all of these, what exactly is this? You can always look that up in the help. Okay, so are we comfortable reading R's help functions yet? Okay, so kind of. So that should always be one of your first places to look. That will always be available. So and it will always be at least reliable. Whereas when you go online and you end up at some place like Stack Exchange, or you ask ChatGPT for help and things like that, sometimes the advice is good, but also sometimes the advice is bad. And at least with Stack Exchange, there's like community voting to upvote better answers and things like that. But you always have to kind of just be a little bit careful reading, someone's answers out there. As hopefully it's good, but maybe not always, right? Even the stuff I tell you, I think what I'm telling you is pretty good and accurate. But it's always kind of good to just kind of double check these things. So, here, so we have S type, a character string indicating what the second argument of statistic represents. The default is going to be I indices, the default, but it can also be specified for frequencies or weights or something. If sim equals parametric, then this is not going to be the case. But I'm going to teach you how to use the default using I here for indices. Okay. So we got data, statistic, R, things like that. And so we're going to do ordinary simulation, and then I for the index here. Okay. So the data argument, you have to specify basically the data that you're going to resample. It can be a vector, it can be a matrix, it can be a data frame. Probably most commonly it's going to be a data frame, because I feel like most of the time in R, that's how we work with our data. It's usually a data frame, but again, not always. And so you can specify a matrix or a vector. And then, but if you are dealing with a data frame or a matrix or something that has this kind of two-dimensional shape, each row is going to be considered an observation. R is the number of Bootstrap replicates. This is usually some big number, like 5,000, 10,000, 50,000, 100,000 or something. Those are just, it could be whatever number you want to specify, 645, sure. But because we're in base 10, 10,000 is like a commonly used value here, okay? And then the statistic this is a function that you will write, okay? It's a function that when applied to the data, it's going to return a statistic of interest, or perhaps a vector containing statistics of interest, all right? This statistic function must take at least 2 arguments. The first argument passed will always be the original data, and the second vector will be a vector of indices, frequencies, or weights. And we are the way I'm going to teach you is using the indices, okay? So again, these are the 3 arguments: the data, the statistic, the number of replicates are. The other ones have defaults. The way the way library boot and the function boot works is that it performs bootstrap resampling in my opinion, a clever way. Rather than resampling the actual values directly, Bootstrap resamples only the indices. And so this allows it to kind of be a little bit faster and more efficient, I think. Okay, it will then kind of, in the statistic function, it subsets the data based on these resampled indices, and I'll kind of show you some code on how these things are equivalent. So remember, in Bootstrap, what we do is we take our kind of data, and we're going to resample it with replacement. And again, that is equivalent to just taking your data, creating a whole bunch of duplicates of it, and saying, this is my entire population. So let's say our population is basically the 26 letters of the alphabet. And let's say I created like 1 million copies. So I've got 26 million individuals, 1 million letter A, 1 million letter B, 1 million letter C, so on and so forth. Okay? And then I want to just draw 10 values from this population of 26. And so a way for me to kind of do that is, rather than having to actually duplicate the letters 1 million times each, I can just sample with replacement. So I'm going to just specify the 26 letters as my population, and I'm going to say sample the population, draw 10 values, and do it with replacement. And when I do this, I end up selecting the letter B, K, Y, O, K, Y, I, U, G, and W. So just kind of by random chance, I end up selecting the letter K twice, I end up selecting the letter Y twice, I select these other letters one time, B, O, I, U, G, and W, and then the other 18 letters of the alphabet just never get selected, right? So there's no letter A, or there's no letter C, or whatever, and that just happens when you sample with replacement. Some values get selected more than once, other values just don't get sampled at all. And so here I sampled directly from that population of 26, and I said I want 10 of these things. Okay. An equivalent thing that I could do is, rather than select the values directly, I could sample the indices. So I could specify the integers 1 through 26, okay? And I can say I want to select 10 of these integers with replacement, all right? And so when I do that, it says you've selected 2, 11, 25, 15, 11, 25, 9, 21, 7, and 23. And we can see that these are the exact same values that correspond to these letters. 2 corresponds to B, second letter of the alphabet. 11 corresponds to K. 25 corresponds to Y. 15 corresponds to O. 11 corresponds to K. 25 corresponds to Y. So on and so forth. And so I can just kind of subset the population of 26 values based on these indices. And again, you can, when you subset, you can provide duplicate indices, and it gets it provides these values. So I end up getting these letters, B, K, Y, OK, the exact same thing here. So rather than sampling the values from the population directly, I could just sample the integers 1 through 26. Now this might seem like pointless. Like this seems easier just to sample the population directly than sampling the integers and then subsetting the population. But the advantage of sampling the indices and then subsetting the data using the indices is that it just allows flexibility, okay? Bootstrap only has to worry about sampling the integers, doesn't have to worry about the exact dimensions or properties of this population or this data, okay? That it's going to leave that up to the author of the functions to kind of make sure that it gets subset properly. All right, so for an example, I guess let me give you your first view quiz answer. I haven't given you any, right? Okay. First letter is E. E as in elephant. E as in elephant is our first view quiz answer. Okay. So for our example, we're going to look at the iris data set. Are you guys familiar with the iris data set? You have seen this before? Okay. It's a very popular data set. I don't know how much I should explain about irises and the iris data set. It's so popular, it has its own Wikipedia entry, okay? And how do I zoom in here? Okay, so yeah, it was kind of first made famous by statistician and biologist Ronald Fisher back in, I guess, 1936 when he started doing stuff on linear discriminant analysis. And it was originally collected by Edgar Anderson, a botanist, okay? But anyway, he looked at 3 species of iris, okay? Setosa, virginica, and versicolor, and we have pictures of these things. We have the Setosa, versicolor, and virginica, and I don't really know anything about flowers, but apparently, how many species of iris are there? There's a lot, okay? No, I mean like out in the world. How many? 310 different species of iris, okay? Whoops. And so anyway, we're just looking at 3 of these things, and these are, this is what they look like. And then, the data set contains things like petal length, petal width, sepal length, and sepal width. And so on an iris, there's often kind of like something that looks like, I just call all of these things petals, but they are not petals, okay? So these 3 that are up here are the inner ones are the petals, and then the ones that are kind of on the outside, and those are the sepals. And so even though, you know, they look like they're all just petals, they're not, right? So some of these are, so if you look at these ones would be the petals inside here, and then the ones that kind of fall out, these are the sepals and things like that. So anyway, so we measure those, and so in our data set we have four numeric variables: sepal length, sepal width, petal length, and petal width. And then we have 3 species: Setosa, versicolor, virginica. We have 50 observations from each of these things. This data is collected and included in here. Okay. And so, you know, just using something like dplyr, I could say group by species and calculate the mean and standard deviation of each of these things. So I can get the mean sepal length and standard deviation sepal length, mean sepal width, standard deviation of sepal width, so on and so forth for petal length, petal width, and so on and so forth. And these are the values that I get. We can plot these as well. So this would be kind of our two-way plot with red dots representing Setosa, green representing versicolor, and blue representing virginica. And a lot of times the data is used to kind of do you have a classification algorithm that can really separate these things? And so if you look at something like petal width, you can really kind of easily distinguish, right? So if your petal width is under basically 0.9, they're almost certainly going to be Setosa, and if it's between 1 and, I don't know, 1.6-ish, okay, then it's almost going to certainly be versicolor, and then greater than 1.6 would be virginica and things like that. You know, some of these other things, like sepal length, there's a lot more kind of overlap, where between versicolor and virginica, there's a lot of overlap here. But anyway, that's what we have here. Okay. So we might want to just perform some basic tests here, and so just to kind of keep things simple, I'm going to just pick one of these variables, sepal length. Okay. So sepal length is basically on the x-axis in these three plots, or on the y-axis for these three plots. And so I want to see, is there a difference between the mean sepal length of setosa and versicolor? Because when you do a t-test, you can only compare two groups. So I'm going to just kind of compare setosa, which are the first 50 observations, and virginica, which are observations 51 through 100. So we're only going to just look at 100 of these dots, basically the red and green dots. And I want to say, is there a difference between the mean of setosa in red and the mean of versicolor in green regarding sepal length? And so it looks like the mean of versicolor is kind of like right around here, and then the mean of setosa is right around here. So we get a mean for setosa of around 5.0, a mean of versicolor of 5.936, are those differences, is that difference statistically significant? So there's quite a bit of overlap as far as individuals go, but as far as the overall mean goes, there is quite a difference here, right? So here we're looking at 5.01 versus 5.94, 5.006 versus 5.936. And that difference of 0.93 between 5.006 and 5.936, that difference of 0.93 is statistically significant, because when you do your t-test, you get a test statistic of -10, around 10 standard errors away from the mean, which corresponds to a p-value of practically 0, 2.2 times 10 to the -16. So basically we're saying, this kind of difference of -0.93 is just not going to happen by random chance if we just use a t-test. Okay. But again, if you didn't want to run a t-test for whatever reason, you can do a bootstrap test. Okay. And so we can do this. I mean, my general recommendation would just be, you've got a big data set, 50 observations, you're doing something that comes from nature, you look at this, it looks like there aren't like crazy outliers, so you don't have any reason to doubt that sepal length is normally distributed. So just use the t-test. There's no sense in making your life more complicated. But this is computational statistics, so we have to make our life more complicated. So we're gonna do Bootstrap here, okay? And so in Bootstrap, we want to simulate the sampling distribution when the null hypothesis is true. Our null hypothesis is that there's no difference between sepal length of setosa, and sepal length of versicolor. That's the null hypothesis, is that sepal length of setosa and sepal length of versicolor are the same. So if the null hypothesis were true, all 100 values, the 50 setosa and the 50 versicolor values, all 100 values are coming from the same population. That's if the null hypothesis were true. This is something I think a lot of students struggle with, because this part feels very uncomfortable, because it feels very wrong. And indeed, in this case, it is wrong, because I think deep down inside we know the null hypothesis is not correct, right? But what you want to do is you want to simulate what could happen under the null hypothesis, that if the null hypothesis were true, how should your data look like? And if the null hypothesis were true, all 100 values are coming from the same population. So what is that population? The population is, we're going to pool all 100 values together. We aren't going to separate the 50 setosa from the 50 versicolor. We're going to just kind of put all 100 together into the same population. And then when I sample my values, so there's 100 values in boot population. When I sample my values, I'm just going to select 50 values out of this population at random, throw them into group A. I'm going to select 50 values at random from the same exact population and throw them into group B. And if we do this, we would expect the mean of group A and the mean of group B overall most of the time to be the same, But what we are interested in is, because of random sampling, they're not always going to be exactly the same. And how different can that be just from random sampling? That's what we're interested in, okay? And so, yes, it feels weird. It feels almost bad, like we're doing something wrong when I say I'm going to draw 50 values from this thing, and I'm going to draw 50 values from the exact same group, or the same population, group A, to create group A and group B. And so again, it feels wrong, but that is the correct thing to do, because that is what we are arguing for if the null hypothesis were true. And we're almost kind of trying to show you that the null hypothesis is wrong, because if you assume the null hypothesis is true, you're going to be doing this thing which feels very wrong, and indeed it doesn't line up. So as expected, when you resample the same population twice, most of the time you get a difference of 0. Okay, you look at the median value, or I guess not most of the time you get a difference of 0, but it's centered around 0. So you look at the median, you look at the mean, the difference that we see is centered around 0. We get a difference of 0.0002698 on average. Out of our 10,000 times, the biggest difference I saw between group A and group B's mean was 0.552. Out of the 10,000 times I did it, the most negative difference I saw between the mean of group A and the mean of group B was negative 0.47. So did I ever get a difference of negative 0.93, which is what I observed? No, that didn't happen. So that to me is a clear indication that after 10,000 attempts, not once by random chance did I ever produce a difference as great as negative 0.93. And so the fact that I did produce a difference of I observed a difference of negative 0.93 indicates to me that these two sets of values are not coming from the same population, right? Because how else could we produce this value of negative 0.93? Because I tried what could happen if we drew them from the same population, and we looked at this a whole bunch of times, and not once did it ever produce a value of negative 0.93. So the fact that I did produce a difference in negative 0.93 indicates that it's the process to produce those values is not this. It's not this, because I tried this thing 10,000 times and I was never able to produce that result. So that would be our argument that the null hypothesis is wrong, because this is what our data would look like if the null hypothesis were true. Okay. Here I manually did this and I resampled my population directly. Okay. I could run the equivalent code, but rather than resampling the population directly, I could resample indices. So here, I'm going to take the same for loop, but I'm just going to modify a couple things. I'm going to sample the integers 1 through 100 with replacement. I'm going to say I want 100 values from the integers 1 through 100 with replacement. And then now that I get my resampled indices, I'm going to subset the original iris data using those resampled indices. So I'm going to do iris square bracket, resampled indices, comma, to indicate that I want to select my rows using my resampled indices. And then I take the first 50 values in my resampled data, put that into group A. Then I take the next 50 values of sepal length of my resampled data and put that into group B. Okay, so there is here I just kind of took all 100 values of sepal length and I created my population here. Here I'm doing something basically the equivalent thing, but this time just resampling the indexes. Okay, so I'm resampling the values 1 through 100, and then I'm subsetting this. When I do that, I get the exact same results. Okay, so there's no difference between this code and this code as far as the results that they produce. But the key here is that I'm resampling my indices. Okay, and the reason why I put this here is because this is how library boot works. When we use library boot, we have to write our own kind of statistic function that resamples the indexes, or resamples the indices rather than the values directly. Okay, but this shows you that, yeah, you get the same kind of median, same mean, max, and in fact, if you check, are all of the values and differences here exactly the same? And it says, yep, they're all the same. Let me give you your second view quiz answer, which is the letter C. the letter C. C as in cat. So when we use library boot, we have to write this function called our statistic function. Okay. Again, how you write your statistic function can differ, but here we're going to say the second argument will be the indices. Okay. Statistic function takes in two arguments. First is going to be your data. Second is going to be something else, and in this case we're going to do the indices. Again, you can kind of specify weights or whatever, but we're going to do the data and the indices. And so the function boot is going to perform the resampling of indices, and it will pass that in as an argument in our function. Okay. And so again, what we want to do is we want to take a look at our 50 setosa flowers and our 50 versicolor flowers and compare the sepal length of those two species here. So this is the function that I'm going to write here. Okay, the function takes in the data. Data is going to be the iris data set, and we get the index. All right, the index argument. The index argument will be resampled indices. That part is done, and what we do is we subset our data. I'm going to say take our data, select our rows, subset our rows using those indices to get our resampled data. Okay. Pay attention to this code and the code that I've written here. They're almost identical. Okay. The code inside my for loop here is almost identical to the code I have inside my function. The key difference here is that inside my for loop, I have this function sample, or the command to resample my values, and I don't have that in here. That resampling of values is handled by the function boot. When you call library boot and function boot, it's going to do the resampling for you and pass the indices, the resampled indices, as your index argument. So I don't have to worry about creating resampled indices. These get passed in as an argument. But once I get that, I subset iris based on the resampled indices, which I do here. I subset my data using my resampled indices that get passed in. From there, I'm going to take my resampled data, select the first 50 values, throw them to group A, take our next 50 values, throw them into group B, which is exactly what I've done here. Okay, take my resampled data, select the first 50 values, throw them into group A and group B. And then the last line here is I just calculate the difference between the mean of group A and the mean of group B, and I have my function return that difference. In the for loop, I take the difference between the mean of group A and the mean of group B, and I store it into the vector differences into position I of my vector. Okay, and that's because I'm running a for loop myself. Package boot handles the storage of the output. So you do this, it returns difference, it just does it for this one resampling, and then it stores the results. So package boot and library boot will handle the kind of resampling of indices and the storage of the outputs for us. But you can see the internal workings of the function are very similar to this for loop over here. So what I do is I call boot. I say the data I want to work with are just the first 100 rows because I'm only interested in my two species, setosa and versicolor. And then I say the function that we're going to use for a statistic is this difference function that I wrote, and I want to do 10,000 replicates. So that's what we do. And we're going to store all of those results into boot underscore results. And we can take a look. This is the output of boot underscore results. It looks like a lot. It's a big list of 11. We get T0. T0 is basically your observed statistic from your observed data. So this would be if you pass the indices 1 through 100, no resampling there. And so basically you get the first 50, which is setosa, the next 50 versicolor, and you calculate the difference between the two groups, and we get a difference of negative 0.93. Right? That's exactly what we got when we just kind of did our t-test ourselves, a difference of negative 0.93, our observed difference between the mean of setosa and the mean of versicolor. T here, these are this creates the sampling distribution of the different indices that, the different resamplings that I get. Okay, so I did 10,000 replicates, so I'm going to get a sampling distribution of 10,000 different randomized differences. R is how many replicates we did. $data is the data that we passed in, which were the 100 observations of Setosa and versicolor. Then there's a bunch of other information regarding the Bootstrap and how it ran, seeds, statistics, sim, blah, 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 blah. We can take a look, okay? I can say, all right, summarize that sampling distribution that it produced. And again, we get very similar results. The mean is right around 0. The largest difference I got between our two groups was 0.506. Most negative difference I got was negative 0.434. Never did I get a difference of negative 0.93. You can call plot. I'm sorry, not plot. I'm jumping ahead of myself. So we can see what is the observed difference that I got between group mean of Setosa and mean of versicolor, and I get negative 0.93. And again, that's stored in boot results, $T0. Okay. And to get my empirical p-value, I can say, well, how many times did my Bootstrap results produce, randomized Bootstrap results produce a value that was greater than the, farther away from 0 than 0.93? And the answer is 0. It happened 0 times out of 10,000. So my empirical p-value is 0. Okay. Now, and statisticians really hesitate to use the word 0, probability 0. The t-test says that probability is 10 to the negative 16, so it's not 0, but on a practical basis, practically 0. I would have to run, 10 to the 16 operations, and I'd blow up my computer because I don't think I have enough memory to store 10 to the 16 results here. I don't know, maybe. Seems like a lot, right? I could create a plot of boot results, and this is what we see, right? We see, as expected, if the null hypothesis were true, the mean difference is around 0, right? Difference between group A and group B, if the null hypothesis were true, is usually around 0, sometimes as great as 0.5, where around 95% are between negative 0.4 and positive 0.4. Okay, and this dotted line represents the difference in our observed data, negative 0.936, and we can see that this dotted line is way extreme compared to our sampling distribution, and we can see, oh yeah, our randomized sampling distribution is never going to produce a difference as extreme as negative 0.93. So this is going to be very strong evidence that our dotted line, our observed statistic, was not produced by random sampling if the null hypothesis were true. So, and this shows that our sampling distribution is normally distributed, which is, I guess, good in this case. I mean, it doesn't really, I guess this would just say, hey, you could have just used the t-test to do your thing. But anyway, that's what we get here, okay? This got cut off, but you can also plot a density curve, and the density curve, if you could see the x-axis, is centered around 0, but we can also see that right here. We can, because we used library boot, there's additional functions. One of them is create Bootstrap confidence intervals. So you can do boot.ci on your results. Here's a little page from DataCamp talking about you doing Bootstrap in R, and this would create confidence intervals for the output here. I get an error, okay? I get an error, and that's because my p-value is 0. So if you recall, creating confidence intervals from your intro stats class, you basically go up or down your standard error. Your standard error is your p hat times 1 minus p hat over n. And so if you ever had a sample where your sample proportion was 0, your standard error becomes 0, right? And then you have no confidence intervals. So that's basically what we're running into, because not a single one of our randomized results were more extreme than our observed statistic. I end up getting a p-value of 0, empirical p-value of 0, and so I can't produce a confidence interval. So I could try something else, and I'll just kind of show you a quick example here. So, let's say we wanted to create a confidence interval for the correlation between sepal length and sepal width. This is kind of a odd thing, and I don't know if you guys. This is kind of like a Simpsons paradox. Are you guys familiar with Simpsons paradox? Maybe, maybe not. Okay. Is sepal length and sepal width correlated? What would you say when you look at iris data? Is there correlation between sepal length and sepal width? Yeah, is it positively correlated or what? Negatively correlated, what? Okay, so if you look at the colors, and if we say, let's look at setosa, definitely positive correlation. Wider sepals tend to have longer sepals, okay? You look at the green dots, also positively correlated. You look at the blue dots, also positively correlated. However, when you put all of them together, so if you were colorblind, okay, and you couldn't see all of these things, and they were all just the same color, it ends up having like a weak negative correlation, okay? So that's this kind of Simpsons paradox, where if you break it down by group, there's definitely positive correlation. But if you look at the whole thing as a whole, if I say, hey, what's the correlation? What slide am I on? Okay, what is the correlation between sepal length and sepal width? The overall correlation of our data is actually negative. It's a very weak negative correlation, negative 0.117, but that's like almost absurd when you break it down by color, right? Sepal length is definitely correlated with sepal width. It's just when you kind of pull everything together. So that's kind of known as Simpson's paradox, where overall you might not see any kind of relationship, but when you break it down, there definitely should be a relationship. But anyway, that's beside the point. The point here is, what do our Bootstrap confidence intervals look like? But this is something you should keep in the back of your mind, something to be wary of and something to be aware of when you analyze your data, is maybe you should split it up and look at that. Here I'm going to just say, let's calculate the correlation of our resampled data. So I'm going to subset my data using the indices. We're going to look at column 1 and column 2 of my resampled data, calculate the correlation. Bootstrap results, most of the time we're getting values of around negative 0.118, which is what we have right here, okay? Values right around negative 0.118. And in this case, I can say, hey, give me confidence intervals. I can say boot.ci of my results, and I get these confidence intervals. It gives me 4 confidence intervals that are all very similar, but also slightly different. It has the normal confidence interval, the basic confidence interval, the percentile confidence interval, the BCA confidence interval. I don't know. What's the difference between these? This is the description of what these things are. The normal confidence interval basically uses the normal distribution. It goes up 1.96 standard errors in each direction, and it estimates the standard errors using basically your bootstrapped t-distribution. So it uses Bootstrap to estimate your standard error. The percentile confidence interval says, hey, we have basically the sampling distribution of 10,000 values. Let's line them up from least to greatest, and let's go for the middle 95%. So out of 10,000, you're going to find rank 250 and rank 9,750. Where are those located? Okay, and you end up getting something very similar between the normal and the percentile thing, which makes sense because the sampling distribution is pretty much normally distributed. The basic confidence interval, what does it say? Computes the differences between the results of each Bootstrap replication and T0, and it reports percentiles based on that. Okay, and the BCA is the bias corrected accelerated interval from B. Efron, kind of a famous statistician, machine learning expert there. And there's an academic journal article explaining this. I have not read it, so I couldn't really tell you the advantage of this bias corrected accelerated interval. It looks pretty similar to the rest. Maybe it's a little bit higher than the others. So I guess it's trying to correct for the bias. I guess for those who are interested, they could read that article. Let me give you your last view quiz answer. Letter B, B as in bear, or bootstrap, okay? And that will be that. Okay, that's it. It's week 9 Friday. Things are wrapping up. Hope your classes are going well. and just a little bit more to go, and you'll have 1 week of spring break. So, all right, have a great weekend, and we'll see you Monday.